Artificial intelligence is hungry. Behind every real-time data analysis and generative AI model sits a physical infrastructure of immense scale, and all that computing power generates an astonishing amount of thermal exhaust. Traditional chips rely on sequential processing. Data moves step by step, forming a queue. We solved this traffic problem by packing billions of microscopic transistors onto silicon, but we're running out of room. The pipeline cannot move data fast enough. Pushing these systems to their physical limits requires enormous amounts of electricity. Keeping these sequential processors running is beginning to strain global power grids to their breaking points. Our most advanced software is now colliding with a hard physical ceiling. We are trying to run the AI era on hardware logic invented over half a century ago. This chart shows the geography of global chip fabrication. The capacity to manufacture these essential sequential processors is highly concentrated. Just a handful of authorities in a few key regions produce nearly all of the world's supply. For a rapidly growing tech economy like India, this concentration creates a massive strategic vulnerability. Relying entirely on imports for foundational hardware exposes the nation to supply chain disruptions and geopolitical leverage. Building the infrastructure to make these legacy chips domestically isn't easy. A single cutting-edge semiconductor foundry requires billions of dollars in capital and decades of specialized engineering experience. How does a country achieve technological independence when the cost of entry for the current race is so high? You don't just try to catch up. You find a way to bypass the sequential processing model completely. Researchers at IIT Bhubaneswar, working alongside universities in Sweden and Japan, recently published a discovery in the journal Nature Nanotechnology that offers exactly that kind of bypass. A moment of wonder. At the center of their research are nanoscale spintronic oscillators. These are tiny magnetic devices that operate entirely without physical circuitry. Traditional chips generate heat by physically shoving electrons through a wire. Spintronics use the quantum spin of those electrons to process information, requiring significantly less friction. Instead of waiting in line, these oscillators behave collectively. In a grid, they naturally synchronize their magnetic rhythms, processing simultaneously. Look at the difference. Sequential methods force a single file line. This synchronized network acts like an orchestra, every instrument playing at once. This behavior removes the traffic jam. Information is processed concurrently across the entire system, without wasting the massive amounts of energy required to move physical electrons. While scientists knew spintronics were highly efficient, they struggled to build large networks. Historically, when adding more oscillators, the synchronization would fall apart into chaos. This chart illustrates the scale of the IIT Bhubaneswar milestone. The team achieved an exponential jump, successfully maintaining perfect synchronization across a network of over 100,000 nanoscale nodes. And they do it incredibly fast. Every single node aligns its rhythm in 45 billionths of a second. Scaling the network to 100,000 nodes provides a blueprint for industrial-scale manufacturing. Spintronics has moved from a theoretical concept into a viable platform for next-generation hardware. A fully scaled spintronic network is exactly what modern software demands. This architecture is custom-built to handle the massive parallel calculations required for artificial intelligence, complex financial modeling, and real-time global data analysis. Because it relies on quantum spin rather than physical resistance, it can execute these massive workloads using a fraction of the electricity required by today's silicon chips. It directly solves the speed limits and the energy constraints of our current infrastructure, making this architecture a logical successor for heavy, high-performance computing. For India, helping pioneer the scalability of spintronics shifts the strategic math. Developing the intellectual property and academic momentum here means owning a piece of the foundation. By establishing the framework for this incoming era of hardware, the nation bypasses spending decades chasing global monopolies in the traditional silicon market. By defining the foundational logic for the next era of hardware, India secures a position of domestic sovereignty. The nation is now setting the terms for the future of global computing.